Hi everyone, it's 1 p.m. sharp at Eastern Time, and let me introduce our speakers. Is Dr. Naru Kaji from National Astronomical Observatory of Japan. Has been conducting observational studies of energetic phenomena in the solar corona, such as solar flare and particle acceleration. He's also actively developing instruments. The projects he has been involved as a Hinode satellite, especially X-ray telescope, CLASP sounding rocket, and FOXY sounding rocket. In FOXY 3, he succeeded in imaging spectroscopy in the soft X-ray band, and based on this success, he is now planning and promoting the FONEX satellite mission with his colleagues for understanding of particle acceleration during solar flares with X-ray imaging spectroscopy. And today he will introduce this instrument as Project FONEX. So please go ahead with the presentation.
Okay, so I'm Noriyuki Narukage from National Astronomical Observatory of Japan. First of all, I would like to say thank you for giving me a great opportunity to speak at the SOLFA webinar. On behalf of the Phoenix team, I would like to explain about our promoting solar flare X-ray satellite mission called Phoenix. Phoenix stands for the physics of energetic and non-thermal plasmas in the X region. Okay, the science goal of Phoenix is understanding of particle acceleration during magnetic reconnection, which occurs ubiquitously in the universe. For this goal, we select solar flares as an observation target, and we set the three scientific objectives. But the first one is to identify particle acceleration site in the reconnection-associated structures in the solar flares. Second one is to investigate the timing of particle acceleration during reconnection-associated phenomena in the solar flares. The third one is to characterize the property of accelerated particle populations in the solar flares. So these correspond to the answer to where, when, how particles are accelerated. Okay, so let's start with a brief explanation of particle acceleration. Plasmas, which can be expressed in terms of temperature, are in the state of the thermal equilibrium, and it exchanges kinetic energy with each other, like this. On the other hand, depending on the surrounding environment, some particles often continue to gain energy and can reach very high energies. This is the particle acceleration. The energy can reach up to 10 to 20 electron volt or more, although there is an upper limit to the maximum energy reached in each plasma environment, but it is a universal phenomenon that has been ubiquitously observed in the universe. However, the mechanism of particle acceleration has not been fully understood. It is known that acceleration in supernova remnant with long acceleration time is due to diffusive shock acceleration mechanism. On the other hand, the mechanism of acceleration in the short time, such as in the gamma ray burst, is unknown. In this case, magnetic reconnection is one of the candidates for the mechanism of this short time acceleration. As you know, magnetic reconnection is a plasma process in which magnetic energy stored in the magnetic field is explosively released and converted into kinetic, thermal, and other forms of energy by reconnecting the antiparallel components of the magnetic field lines. So this magnetic reconnection has also been observed ubiquitously in the universe. This is a diagram for magnetic reconnection proposed by Zi and Dalton. So in this diagram shows a plasma environment in which magnetic reconnection occurred. So horizontal axis shows a size normalized by the skin length, and the vertical axis shows a Langston number. The solar flare is located at the center of this diagram, and the sun and the high energy object are located in a common area called the multiple X-line hybrid. Additionally, the flare and the space plasma have the almost same Langston number, so it is easy to compare and contrast each other. So this is one of the drivers for us to study the particle acceleration with a solar flare. Another reason to observe solar flare is Sun is the only astrophysical object that can be observed in space and spatially and temporally resolved with a wide field of view. In addition, high energy particles and electromagnetic waves such as X-rays generated by solar flares have a great impact on the space environment around the Earth, which is important for the space weather point of view. And next, I briefly introduce the current status of our understanding of solar flares. It is well established that solar flares are driven by magnetic reconnection, both observationally and theoretically. In a solar flare, magnetic energy stored in the corona is divided by magnetic reconnection into kinetic energy of the mass of plasma, such as coronal mass ejection, the thermal energy of heating of coronal plasma, and non-thermal energy, such as kinetic energy of accelerating particles. The most interesting part is the ratio of the energy distribution. A statistical study by Ashwani et al. Estimates that about 50% of the released magnetic energy is used to accelerate electrons and 20% to accelerate ions. In other words, solar flare is a very good accelerator that can use most of the released magnetic energy to accelerate particle. From an energy budget perspective, understanding particle acceleration is essential to understand the solar flares. However, the actual energy conversion of solar flare is not as simple as this. In reality, solar flares produce various plasma structures, each of which can act as an energy converter and accelerator. In other words, to understand the particle acceleration in magnetic reconnection, we need to understand them as a system. However, at present, we know that solar flare accelerated the particle, but we do not know exactly where acceleration takes place. Thus, the particle acceleration remains an important unresolved problem in the solar physics. There are two reasons for this. So reason one, the first reason is a lack of capability of the existing instruments. So as you can see in this figure, we have not been able to obtain any information, especially in the area of the energy distribution. And the second reason is there is a large gap, both space and time, between the MHD scale of the plasma structure and the kinetic scale of the accelerating particles. For this reason, various models have been proposed, but no definitive solution has been reached yet. In the Phoenix project, we overcome this situation by taking 3 approaches, such as new observation, new theoretical model, and interdisciplinary collaborations. Okay, so let's start the new observation. So this figure shows a particle, so the picture of magnetic reconnection in a solar flare and the flow of the accelerated particles. As explained earlier, to understand the particle acceleration, we need to understand the solar flare as a system. To do so, we need to observe at least all 4 zones, as shown in the figure. Zone 1 is a region containing the energy release site due to magnetic reconnection, from which accelerated particle may originate. Zone 2, where the accelerated electron collide with dense flare loops, and it is also candidate for the acceleration site. So zone 3 is where particles pass through, and zone 4 is where they hit the solar surface and lose their kinetic energies. However, if mirroring occurs, particles will bounce off at the zone 4 and trapped in the zone 3. During the trap, secondary acceleration may also occur. However, most of the current observations are only zone 4, and depending on the type of flare, zone 2 can be observed occasionally. Therefore, Phoenix will perform plasma diagnostic for all zone 1 to 4. Specifically, we will perform space-time and energy resolved observation for all 4 zones. In this way, we can obtain information on the thermal component at each location, as well as physical information on the non-thermal components, such as accelerated electrons. By doing this, we can find where the acceleration is dominant and associated plasma phenomena. In addition, plasma structure changes rapidly in an Alfvén time scale of the solar corona, which is about 10 seconds. It is also extremely important to track these time variation. So this movie shows a time variation of the solar flare spectrum as captured by the US CubeSat MINX in a soft X-ray range and LESI in hard X-rays. So MINX does not have a spatial resolution, but this data fully illustrates the importance of the obtaining the spectra at a 10-second intervals. Phoenix will acquire this time variation with a spatial resolution. So we will then use a spatially and temporally resolved spectral information to examine the energy transport and to determine the budget of the understanding of the particular, to determine the budget like this for understanding the particular acceleration. Additionally, we will measure the polarization to investigate the anisotropy of particle motion, as will be explained later. So in this slide, I explain why Phoenix will observe the soft X-ray to soft gamma ray band. So it is important to obtain the information on the electron populations under the accelerating and the electron populations already accelerated, as well as information on the plasma phenomena that are candidates of the acceleration agent. So this and this capability is important. Therefore, observation in X-ray to gamma ray band is essential. Of course, joint observation is very important because EUV band and radio observation provide us a complementary data set, and especially so in from the radio, so we can obtain the coronal magnetic field information. Okay, so in this slide, I will explain the novelty of Phoenix in observing solar flares in the X-ray to gamma ray band. First of all, the imaging, the improved dynamic range allow us to observe the old zones like this. So in an existing soft X-ray observation, we are using the CCD for the imaging. But when observing the energy release region, the exposure time is too long for the flare. But when observing the energy release region, it's a dark region. In such case, exposure is too long for the flaring group, and the blooming occurs like this. And due to the blooming and the scattering light, the energy release region could not be observed sufficiently. On the other hand, in hard X-ray observation, indirect imaging using the modulation collimator is performed. And the energy release region suffer from the noise and cannot be observed clearly. So Phoenix solved this problem by focusing both soft and hard X-ray with mirror, and imaging spectroscopy with a high-speed camera with a CMOS and CAD-TEL detectors. The second is imaging spectroscopy in a soft X-ray band. In the soft X-ray, we can obtain the information on the plasma phenomena that are the candidates of the acceleration agent, and on the electron population and the acceleration. In this way, we can obtain precise information on high energy plasmas produced by flare. So this is data Phoenix will be taken. So in the hard X-ray to soft gamma ray band, we will perform the polarization observations from in this range from the 60 keV to 300 keV. So although this observation does not have a special resolution, but we can obtain the polarization information, including the anisotropy of the electron motion and the highest achieved energy, which supports the imaging spectroscopy data. So now, there have been some attempts to measure the polarization with a LESI satellite, but the instrument was not originally designed for the polarization observation. But the Phoenix will start the practical polarization observation like this. So even in N-class flare case, it is expected to obtain this kind of the polarization. So this figure shows a spectrum during the solar flare and the energy band covered by Phoenix. So this is a new innovation of Phoenix. In a soft X-ray and a hard X-ray, we will perform the imaging spectroscopy. And in a hard X-ray to soft gamma ray range, so we will perform the polarization measurement. And now we are continuing our development to be able to observe higher energy range more and more. So this table summarizes specification of Phoenix and the rationale for them. The slide will be made public, so please check it later. And so here is an overview of the Phoenix satellite. The instrument consists of the soft X-ray imaging spectrometer for 0.5 kV to 10 kV, and a hard X-ray imaging spectrometer for 5 kV to 30 kV, and soft gamma ray spectrometer for 20 kV to 300 kV and above. The soft and hard X-ray system are realized by the combination between the high precision X-ray mirror and the high-speed camera. And the soft gamma ray instrument will consist of the Compton camera, like Xiaomi satellite, and active seal. This instrument can measure the polarization above the 60 kV. And this satellite to carry these three instruments can be realized using the flexible standard bus system for ISAS JAXA small scientific satellite series. And some of the key technology for Phoenix has been developed and demonstrated using the opportunity of the FOXY sounding rocket series. Starting with hard X-ray observation, we have added a soft X-ray instrument. And FOXY 4, scheduled for launch in 2024, will finally take on the challenge of observing solar flares. So this figure shows photon counting data of the soft X-ray acquired by the FOXY 3. With the progress of the CMOS detector technology, we have achieved the photon counting measurement in the soft X-ray band for the sun. So this movie shows the data from the high-speed continuous imaging of the 250 frames per second. So each white dot corresponds to the individual X-ray photons from the sun. For this data, we can obtain the position, time, and the energy information for each individual photon. Therefore, it is possible to create an imaging like this by arranging the photons. And we can also track the spectrum and the temporal evolution. So I can show you some example. So this is actual data and software which I made. So this is a sun. So during the FOXY flight, FOXY gets more than 10 million photons. So using the 10 million photons, so we can create this kind of the full disk image. But this is not a simple image. So this is this image have a rich information. For example, so we can create a spectrum in each region like this. So additionally, so we can track the temporal evolution of the spectrum. So I think this is a great advantage of this kind of the data set. Okay. Okay, so as I explained, the observation time of the FOXY was about 6 minutes, but we obtained 10 million photons information. And I developed this kind of the data analysis system. And now I equipped spectrum fitting to capability with the XPEG. Okay. So the sorry. So this is a sorry. Yeah. So the data analysis is carrying out using the XSpec as I explained, and tool for analyze. Sorry. Sorry. So I make a mistake. Okay. So let's move the next slide. Okay. So so the next step is to observe the solar flares. FOXY4 has been selected by NASA with the highest ranking of excellent, and it is scheduled to be launched in the 2024. PI is Lindsay. And for the flare observation with sounding rocket, we will monitor the solar flare in real time by keeping the launch vehicle in a standby mode. And just after the flare occur, we will launch the rocket. So this is the first time for NASA to operate this type of the flare observation with a sounding rocket. So in this flare campaign, HISI flare also will be launched simultaneously with FOXY4. So since FOXY4 will observe flare, it is a great opportunity to demonstrate Phoenix, not only in terms of science, but also in terms of the observation technologies. Both mirror and the detector are currently being updated for solar flare for FOXY4. Now in Japan, the high precision electroforming mirror is being developed by Nagoya University, and the CMOS camera is developed by NAOJ, and the CAD-TEL detector was also developed by the University of Tokyo and the Kavli IPMU and ISAS. And the spectral resolution will be improved like this. So this is a FOXY3 image, and but in a FOXY4, we can obtain this kind of the very clear solar flare image. So this electroformed mirror and the CAD-TEL detector will be used for the hard X-ray observation of the Phoenix. Okay, so in addition, key technologies that will not be used in FOXY are being evaluated using the synchrotron radiation. So this is the result of the development of a glass-polished high-precision X-ray mirror for soft X-rays, which is being developed at ISAS. And a prototype of the mirror with low scattering and a high spatial resolution has been completed. So this is a result. So, so the performance of the mirror alone is less than 1 arcsecond. And the scattered light is significantly suppressed like this. So then using this mirror, we can achieve the very good dynamic range to clearly observe the dark energy releasing region against the bright flaring loop. And so this is a XRT image, but after Phoenix we launched, we can obtain the soft X-ray image like this or more better. And we can obtain the hard X-ray image like this in this image quality. And next, I explain the Compton camera system. We have already installed the soft gamma ray detector on the Hitomi satellite. So we will use the heritage of this detector. But we are modifying some parts of it for the solar flare observation. And we are also planning to use active shield as a detector, so which will allow us to observe up to the MeV band. Okay, so next I explain the numerical approach. So using in this approach, so we will fill the gap between the MHD scale and the kinetic scale. So this is a magnetic reconnection diagram again. And progress in computing technology have made it possible to perform the calculation closer to reality. And the Phoenix takes both MHD and particle approaches like this. So this slide illustrates a strategy. Using the MHD calculation, MHD calculation are used to follow the global energy release of solar flare and the associated change in the magnetic and the velocity fields. By adding the test particle, so we can examine the acceleration and confinement of the particles in the global dynamic magnetic field. On the other hand, at the MHD scale, we cannot follow the micro-scale physics, such as wave particle interaction. So we plan to use a particle model here. But how to include this effect is a big challenge. So, for example, we pick up the location, we pick up the local region and study the acceleration trapping process using the kinetic models. And additionally, so we are also working on the emission model to compare these numerical calculations with observations. Okay, so I show the some example. So this movie is a MHD calculation of the solar flare. So it is a method that has been greatly developed in the solar flare research, and it is suitable for creating the global structure and investigating and their development. And the largest number approaching those of the real solar flare condition, and we are able to create a variety of plasma structure that has been found in the observation like this. So, for example, this is what it looks like. So, there are structures that can be an agent of the acceleration of the particles. However, since this calculation is based on the fluid approximation, the motion of the particle cannot be traced. So we are now working on adding the test particle to the structure calculated by MHD. This is a result of the calculation by Dr. Kaneko at Nagoya University. Although the MHD structure is still a snapshot, but we are gaining a new insight into particle acceleration and confinement by investigating various phase and location like this. So such calculation can be also done in 3D in a realistic magnetic field structure restricted by observation. And in addition, we are studying the constructing the emission model to compare numerical result with observation. This will allow us to convert electron spectra obtained by the numerical simulation into the photon spectra obtained by the observation. This is being carried out in collaboration with the high energy astrophysics group. So Phoenix will explore the physics of particle acceleration through iteration of the novel X-ray observation and the numerical simulation with macro and micro connections. Okay, so the third approach is interdisciplinary collaboration. So Phoenix is collaborative project among 4 research fields: solar, high-energy astrophysics, space plasma physics, and laboratory plasma. Each of them is in charge of their own area of space. Own area of specialty. Okay, so this trend is similar to sulfur, I think. So Phoenix project can contribute to and collaborate with 6 science subjects of the sulfur, like this. From here, I will introduce the extra science. In solar research, Phoenix can approach not only acceleration, but also heating and radiation topics. If we focus on heating or summarization, we can contribute to the coronal heating problem. And if we focus, if we look at the direction outward from the sun, we can contribute to the field of space weather, such as coronal mass ejection and impulsive SEPs. And the Phoenix will also able to observe objects near the ecliptic plane and can be used in the collaboration with the X-ray astronomy instrument. In addition, since Phoenix can provide the new quality of X-ray observation data in the sun, namely imaging spectroscopic data, we believe that it will be able to develop new research, for example, on scale law, including other space plasma environments. So this is a schedule of Phoenix. So this is today. So I think next AO will be issued around 2022. And Phoenix is a plan to be launched in the solar cycle 26. It means around 2030s. Before that, we will launch the FOXY4 as a demonstrator of the Phoenix in the science and instrument development point of view. And in 2026, SolarC EUVST will be launched. So from the EUVST, we can obtain the rich information for the solar flare. So we hope we can perform the simultaneous observation between the EUVST and the Phoenix. So this is our strategy. Okay, so this is a summary slide of the Phoenix, one-page slide of the Phoenix. Okay, so finally, so I want to announce our workshop. We are now organizing the IPMU, Kavli IPMU workshop. The title is Particle Acceleration in Solar Flares and the Plasma Universe. So now we are opening for the registration and the abstract submission. So if you are interested in, please join this workshop. So that's all. Thank you very much.
Okay, thank you very much for your talk and for nice timing. So we are now open for questions, comments. So please either raise your hand or you may want to just unmute and ask questions. Hugh?
Oh, thank you. Thank you.
You're unmuted, so just please go ahead.
Okay, well, thank you. Hello. Thank you for a nice overview. The question I have is what is the imaging capability for polarization?
No imaging capability for the polarization.
Ah, okay.
Okay, other questions?
Gregory, can I ask one? This is Jim Drake. Hi.
Sure, go ahead.
Yeah. So one of the challenges we've found in we've been working hard on actually comparing some of our new modeling efforts with the September 10, 2017 event. And one of the challenges we found is in trying to figure out what the inflow and outflow velocities are for that event. And part of the problem, I think, is the cadence on the EUV measurements is sort of marginal in terms of being able to measure the relevant velocities. So I'm wondering in Phoenix what the capabilities are, for example, to be able to determine bulk flows, speeds, and that kind of thing, and what's your cadence for doing that, so that you can try to diagnose not just the spectrum of energetic particles, but trying to figure out what the alphanic flows are really like in the vicinity of the energy release site.
So Phoenix will perform the continuous exposure. So if a photon number is enough, so we can create the image in a very higher temporal resolution. So it depends on the flux, of course. But Phoenix is not a simple imaging. So Phoenix will, so for example, this is the data. So we can change the temporal binning like this. So as we want to do. So in a, for example, in an extreme case, microsecond cadence is possible. But as you can see, so flux is not enough. So it depends on the flux and the instrument. If I get the rough number of the density and the temperature of the such structure, so we can estimate how rapidly trace such structure using the Phoenix in a good image quality.
Okay. So, Jim, is it satisfactory, or just you have a follow-up comment?
No, I just so I guess I wasn't sure whether the data in the soft X-ray regime would also be able to be used to figure out the bulk flows that might be taking place, or whether they are using other ways of trying to look at the EUV data to determine this kind of thing.
Okay, other questions? I think that
another technical, if it's okay.
Yeah, okay, go ahead. Yeah.
Another technical question about Phoenix is the question of how you would handle the dynamic range, image dynamic range. This is a big problem across the spectrum because it's so steep, and so I'm wondering what techniques you will use and what dynamic range you can expect to get.
Okay, so yeah, it's yeah, thanks to the very high precision X-ray mirror, so we can achieve the high dynamic range. So this is a measurement result from the glass polished high precision X-ray mirror. So for example, so once away from the 1 arc minute, so scattered light is suppressed to 10 to minus fifths. So this means even if there is a bright flaring group here, so such effect is significantly suppressed in a region away from the 1 arc minute. So then, so we can observe the coronal area.
Right, but I'm
So-
interested in the flare itself. So in the flare itself, how bright a flare can you detect, or how faint a flare can you detect in the flare pixel?
Sorry, say again.
So the flare observation itself, maximum and
Mhm.
minimum counting rates, what do you expect to see?
Okay, so so detector performs a continuous exposure, and to do the photon counting, so we should limit it. So we should limit its incident photon flux about 1% or so. So solar flare is very bright, even in a small flare. Anyway, so we should insert the attenuation filter to control the flux. So then, so we can observe the from the roughly say C class flare to X class flare by controlling the attenuation filter.
So a series of filters, or one filter, or and
Ah.
the whole image has the same filter, right?
We plan to deploy the filter foil, so then we plan to equip the various types of the filter to adjust the wide range of the flare.
Okay.
Okay, good. I had a question, another maybe technical question about FOXY 4 sounding rocket experiment. So you mentioned that this will be like to observe flares, but the flight itself will be possibly relatively short. So could you comment what will be expected duration of the flight and strategy to catch a flare?
Just a moment. Sorry, written in Japanese, but yeah, we will do the real-time monitoring and Gauss flux in, for example, using the Gauss flux, and then Gauss flux exceeds a certain level, we will launch the rocket, and so then we cannot observe the impulsive phase, maybe from the peak of the flare or decay phase. So we can, yeah, FOXY will observe. That is a limit of the sounding rocket opportunity. So then, we need a satellite to observe the impulsive phase where acceleration is significantly occurred.
Okay, good, thanks. Any other question? Satoshi, please go ahead.
Okay, so can you hear me?
Yeah.
Okay, so yeah, thank you very much, Narukagi-san. So very nice talk. So yeah, I have one question about our numerical simulation part. So yeah, so did your team conduct a particular test particle simulation on the background magnetic field, which is obtained from the MHD simulation, right?
For this simulation?
Yeah, the background field is made by the MHD simulation, right?
Sorry, so Kaneko-san did such simulation, so I'm not so familiar. But yeah, I guess this magnetic field is made by.
Okay. So what do you think about non-MHD effect? So for example, Hall effect or something. So is it? I think is it important to accelerate a particle? So what do you think? So in future, so you will take into account the non-MHD effect, right?
Yes. So that is a very important thing. As you mentioned, so in a MHD regime, so we cannot treat the entire physics, especially for the microphysics. So microphysics. So yeah, we should consider the new development to treat such one.
Okay, you will take into account the
Yeah.
non-MHD effect.
Yes,
Okay,
yes.
thank you very much.
But sorry, but I'm not the expert for the numerical simulation. So
Okay.
then, so my colleagues will do that. Sorry.
Thank you very much.
Good. Satoshi, do you have one more? You just
Yeah, no. Sorry.
let me lower your hand. So, do we have other questions or comments? In fact, I do not see any raised hand or unmuted microphone. So, if there is no question or no comment, so let me thank our speaker again for interesting presentation and interesting perspectives in high energy physics, long term. So thank you very much. And okay, great. Thanks, Jim.
Thank you very much.
Yeah, so please, Jim, are you raising your hand? Jim, just go ahead and
Sorry,
say
I was
something.
just gonna clap and I pressed the wrong button. Okay, very
Okay,
nice
so you
talk.
just
Thank you.
support what I'm saying, I believe, yeah? So thank you very much, and let's meet in mid of October for the next colloquium. So thank you very much, and see you next time.
Yeah, thank you very much.